All right, the first problem says 1 kilogram of refrigerant fills a 0.090 meter cube rigid container. So I would start with sketching. And this is a rigid container, meaning that volume doesn't change with energy interactions. And it is given to me. And mass is also given. And this is a refrigerant. So it is important to write these things down to see the picture clearly. So initially the temperature was minus 30 degrees Celsius. The container is then heated until the pressure is 240 kilopascal. Determine the initial pressure, okay, and the final temperature. So since certain information is given to us and the properties of the system is being asked, I should be able to look at the tables to figure out the properties. Of course, we need to look at the right tables, right? So about the first state, they give us temperature, and they didn't give any other specific property that would help us to look at the tables, but they give us volume and the mass, and I should be able to calculate the specific volume from there. So at first state, the specific volume is the total volume over mass, which is 0.090. So specific volume at the first state is 0.09 meter cube per kilogram. Okay, now regarding the first state, now I know the specific volume in addition to the temperature. Right? And this helps me to be able to look at the right tables and read what the pressure is going to be. Let me see. Determine the initial pressure and final temperature. Okay, I'm sorry, they said the final temperature. Okay. So in that situation, let's look at the tables. Knowing this is a refrigerant, I need to look at the refrigerant tables. What I would do is first look at saturated refrigerant tables. And at that temperature, where is my specific volume is located? Is it in between VF and VG? Let's see. Okay, so the tables, refrigerant for minus 30, right? So I'm sorry, it's gonna take us some time to find the right page. Okay, so refrigerant tables, we are looking at minus 30. Let's see, where is it? Here. And VF and VG are given here. So I'm gonna write them down to my page. So VF Okay, when I compare my specific volume with these values of saturated liquid and vapor specific volumes, I notice that the volume fits in between. That means I have a mixture, right? Because our specific volume at the first state is in between VF and VG. That means at the first state we have a mixture. Okay, good. Now, what does that mean? Because they're asking for the pressure. That means that at this temperature, the pressure has to be saturation pressure, because otherwise we wouldn't have a mixture. There wouldn't be a phase change going on. So therefore, the pressure at the first state should be the pressure, saturation pressure at -30, for us to be able to have a mixture, because at that temperature the only way you can have a phase change is to be at the saturation pressure. So now I'm going to go back to the table and read the saturation pressure in terms of kilopascal, which is 84.43. So this is the first part, right? Now the next thing they were asking is find the temperature at the second state, the final state. And again, we should be able to look at the tables, but we need to look at the right tables. Now for that we need to have two intensive property. Well, we are given the pressure, okay, but it looks like they don't give us anything else. Let's see, it was 240 kilopascal. It looks like that, but they actually give it to you because they said it's a rigid tank. Rigid tank, oh, let me see, what did they say? Yes, so they said it's a rigid tank. That means that since volume and the mass is not changing because it's a closed system, then a rigid tank, therefore specific volume should not change either, right? Looking at the formula, this doesn't change, this doesn't change. Therefore, we can say that specific volume is also not changing, which was, where is it? 0.09. Okay, so now that means we can look at the right tables to read what the temperature is. But which tables we gonna look at? Again, we are starting from the saturated refrigerant tables. At that pressure, let's see what is the VF and VG. So we go look at the saturated refrigerant pressure table, and the pressure is 240 kilopascal. Where is it? It's here, right there. And then this is VF, this is VG. Our volume was 0.09, right? That looks like 0.09 is bigger than VG. So saturated vapor specific volume. So since your specific volume is bigger than VG, that means you have super heated vapor. Now you need to look at the right tables. We need to look at superheated tables, which is table A13. Here our pressure was 240 kilopascal, which is 0.24 megapascal. And let's locate that. It's right there. And now we are looking at the temperature, right? That is corresponding to 0.09 specific volume. So I see a number here under the specific volume column, which is very close to mine, right? 0.09. So approximately, therefore, I can read the corresponding temperature to be around 10, okay? 10 degrees Celsius, I can say that. Or if you want exact value, if you can also do linear interpolation. Approximately 10 degrees Celsius. Okay. All right, the question says 10 kilogram of refrigerant at 320 kilopascal fills a rigid container whose volume is 14 liter. Okay, so again, we sketch our system. Okay, and it's a rigid tank, it's a refrigerant. We write down what is given. We are given the mass, and it's a closed system, mass doesn't change, and we are given the pressure and also the volume in terms of liters. So we can convert this to meter cube. Okay, so the container is, okay, so let's see, determine the temperature and total enthalpy in the container. Okay, so temperature and the enthalpy. The container is now heated until the pressure is 600 kilopascal. I'm sorry. Okay, it says determine the temperature and the enthalpy when the heating is completed. Okay, so like this. Like that. All right. So let's start. Since they're asking enthalpy and temperature, these can only be found looking at the tables, because they're asking the properties of our system, and we can look at the right tables from what is given to us. And let's analyze what is given to us at the first state. So at the first state, they give us pressure, but we need one more intensive property to be able to look at the tables. So that would be the specific volume, because they gave you the volume and the mass, and you should be able to calculate it, what the specific volume is. Very good. So once we figure out the specific volume, we have the pressure, we should be able to figure out which tables are going to give us the right values for our properties. So first of all, remembering this is a refrigerant, we need to look at the refrigerant tables, and with the pressure of 320. Let's go here. Okay, so we read VF and VG. Very good. Let's go back and see our specific volume is 0.0014. So it looks like this value fits in between. Okay, so that means we have a mixture. So very good. And so if you have a mixture, that means you need to be at the saturation temperature at that pressure. Otherwise, you wouldn't be having a mixture or a phase change going on. Therefore, I'm just going to read the temperature to be 2.46 degrees Celsius. Okay. The next thing they ask is the total enthalpy. And to be able to find that, all we have to do is read what is the enthalpy at that state, right? But the enthalpy cannot be read directly from the table, because we have a mixture and I need to calculate it, and I can only do it with a quality. So I need to find the quality at the first state to be able to calculate enthalpy, specific enthalpy first. And of course, to be able to calculate the quality, I need to use a known specific property. In this case, it's specific volume, because that is what we know, okay? So I can use this equation. Or in other words, Vg minus Vf. We can use this equation to calculate the quality. Of course, I need to know what is Vf and Vg. To do that, I go here and remember these values that we just read, okay? And then let's plug these into the equation. All right. This was our mixture's specific enthalpy, specific volume, I'm sorry. This Vf is what we read from the table. And Vg and Vf we also read from the table. And after your calculations, it is 0.0099. The quality should be a value that is in between 0 and 1. And now it's probably correct, okay? After you check your calculations again, just make sure it is correct, okay? Now we know the quality. Now we can calculate enthalpy, specific enthalpy, using quality, right? Here, this is we calculated. This and that we read from the same table, okay? Let's go HF and HFG. All right, now going back, we're gonna calculate it. So let me open a new page here, okay? So it says, okay, add a page. I couldn't figure this out. Anything. That's how I do it, okay. I'm sorry. Okay. All right, so we are solving it now. Just plug in the numbers, right? Okay, let's plug those in. 55.14, 0.0099 times. Okay, and if you do that calculation, it should be 57.1 kilojoule per kilogram. And the units of enthalpy you can read from the table. And of course this is a specific enthalpy. Okay, so we found specific enthalpy to be 57.1. They asked for the total enthalpy, so that means we need to multiply mass with the specific enthalpy. Mass was, I think it was 10 kilogram, right? And 57.1 kilojoule per kilogram should give us the total enthalpy in kilojoules. Okay, so we found the enthalpy too. All right. Now let's take a look at the second state, because they ask the same thing for the second state. And remembering what we know at the second state is we are given the pressure, and we should also know the specific volume because it's a rigid tank. Okay, let's write it down. I think that is correct. Let me check. Okay, so now what we need to do is basically, so let's look at that pressure. It was 600 kilopascal. Where this fits, 0.0014. It looks like we again have a mixture. Okay, this seems like a long question. All right, now to do, be able to calculate the enthalpy, and then what else they needed? Temperature. It's easy to figure out the temperature because it has to be the saturation temperature at that pressure. So it let's look at what is the saturation pressure at that temperature. T2 is equal to T saturation at 600, because at that pressure, if there's a phase change, that means you need to be at that pressure. You need to be at that temperature, right? So at 600 kilopascal, the temperature has to be 21.55 for you to experience a phase change, basically boiling, right? So this has to be your temperature. We found this. Now to be able to figure out the enthalpy, we again need to do calculations here, starting from calculating the quality. Okay. All right, VF and VG. Again, going back, you need to read these values for VF and VG. Let's plug those in and calculate what the quality is. Let me check one thing. Okay. I think that was the value. Okay, good. Right, and then quality should be 0.01731. Okay, good. Now again we do the same thing. X2 HFG. Now you go back and read HF and HFG from the table at that pressure and plug those values in. Okay, just like I showed you, right? And you should find specific enthalpy to be 84.464. Now to find the total enthalpy, we need to multiply this with the mass. And that is your answer. All right. We have a rigid tank and its overall volume is given. It has a water steam at 220 degrees Celsius. Now 1/3 of the volume is in liquid phase. Okay. That means it's a saturated liquid, and the remaining 2/3 is we have vapor. Now it looks like this is a saturated vapor and saturated liquid mixture. Okay. What is the pressure? What is the quality? And what is the density of the mixture? Well, the pressure is easy because if you have a mixture, it has to be the saturation pressure at that temperature. Okay, now this is water, so I need to choose the right tables, saturated water tables, and find the right temperature tables 220, and the saturation pressure is corresponding saturation pressure is 2319.6. Okay, well, we found the pressure. Now next they're asking us to find quality. Well, if they are giving you the ratios of the saturated vapor and liquid, because it will help you in your calculation for the quality. In fact, if you know another way besides using specific properties, another way to calculate quality is if you know the mass of the vapor, you can divide it to the mass of total, right? And in this situation, we can actually calculate these things because we know that if I know the specific volume of the saturated vapor and multiply it with the mass of the saturated vapor, it will give me the overall volume of the saturated vapor. So therefore, if I want to figure out what is mg, then I should be able to use this formula, right? It looks like I would be able to calculate the volume of the saturated vapor, and specific volume of the saturated vapor at that temperature can also be read from the tables. So let's calculate it then. This is 1.8 is the overall volume times 2/3 of it is vapor, remember, and Vg is, we look at the same table, Vg column is right there, right? It is 0.086094. Okay, so it looks like you can do this and calculate this to be 13.94 kilogram. All right, we can do the same relation, same equation, we can use it to calculate the mass of the liquid. And this time, this is gonna be 1/3. And the specific volume of that saturated liquid, you read it as this, it's VF. Okay, and this will give you 504.2 kilogram. All right, now the total mass should be the sum of the mass of the saturated vapor and mass of the saturated liquid. Okay, so we found this. Now we can use this to calculate the quality, right? Because it was mg over mt, which is then 0.0269. Okay, so we know the quality now. Now, knowing the quality is good because that's what they were asking, and we can also use it to calculate properties too. Let's see what they're asking. What else? So we found this, right? And the next thing is they're asking density. So if you can remember what density equation is, density is equal to 1 over specific volume. Okay, because the specific volume unit was meter cube per kilogram, and then this is kilogram per meter cube. So it's the reciprocal of the specific volume, right? Now, that means if we know the mixture's specific volume, then I can calculate the mixture's density. And since it's a mixture, to be able to calculate its specific volume, I need to use quality. That is good since we were able to calculate this already. So let's plug the values in then, remembering VFG is VG minus VF, and let's read VF and VG from the tables. Okay, these are that values we previously read already. Let's plug everything in and calculate the specific volume of our mixture. This is Vg minus Vf, and density is then 288 kilogram per meter cubed. 1 kilogram of water vapor at 200 kilopascal fills the 1.1989 meter cube left chamber of a partitioned system shown in the figure. The right chamber has twice the volume of the left, and initially it is evacuated. Determine the pressure of the water after the partition has been removed and enough heat has been transferred so the temperature of the water is 5. Okay, I think there's something wrong with the wording here, but that means they are after removing the partition, the temperature, heat is transferred in so that the temperature inside is 5. Okay, so let's analyze it now. We are given it's a water, first of all, our system is, and mass of the water is given. Let's write down. They also give us the volume initially. And they also give us the pressure. Okay. All right. So here what we can do is, since volume and mass is given to you, I would understand that we can calculate the specific volume here, and with the specific volume and the pressure known, we would be able to look at the tables to figure out the properties. Okay, so let's write down. I can calculate specific volume because I know the total volume and the mass, and that is 1.1989 meter cubed over 1 kilogram. Specific volume initially is 1.1989 meter cubed per kilogram. Okay, now you know the pressure and you know the specific volume, and you know this is a water, and you should be able to look at the tables and figure out properties. But let's see what they're asking for first. They're asking for us to calculate the second state pressure, right? And to be able to look at the second state, I should be able to know properties about the second state. And here what I know is, initially the volume on the left was basically 1/3 of the overall volume, right? So that ratio that I know, because the evacuated space was twice the volume that is on the left. So I know the ratio of the volumes occupied initially. So what I can do is actually multiply this with 2. Actually, if I multiply with this with 3, I can find overall volume, right? Because this is 1/3 and this is 2/3. Okay. So if I already find the overall volume, I can just multiply this with 3. Okay. I'm sorry. So since now I know the overall volume, and I know also the mass, because mass doesn't change, because the mass of the water, they're not adding water or getting out water. This is just a closed system. We're removing the partitioning. So the mass of the water inside is 1 kilogram, but now it's occupying space 3 times of the initial volume once they remove the partition, right? So what I can do is calculate the specific volume at the second state, because I know the overall volume, right? And also I know the overall mass, which is 1 kilogram, which gives me the specific volume of the water once the partition has been removed. So that is the specific volume. The other thing they gave us about the second state is the temperature. Okay, they said it is 5 degrees Celsius. So I know the specific volume, I know the temperature. Now I can look at the tables to read the pressure. Okay, let's go to the tables, water tables, and we are given 5 degrees Celsius. Let's look at 5 degrees Celsius. Let's choose this color, 5, right? And what we need to do is we know our specific volume is 3.5967. I can compare that with VF and VG. Okay, let me delete these. All right. Looking at VF and VG and comparing it with our specific volume, which is 3.5967, it looks like it fits in between. So it is bigger than VF and smaller than VG. That tells you that you actually have a mixture. That is good, because if you have a mixture, you have to be at the saturation pressure at that temperature for the boiling to be taking place. So therefore, we can say our specific volume is in between VG and VF at that temperature. So we actually have a mixture. And since we have a mixture, the pressure has to be the saturation pressure at that temperature, and we were able to read it from the table. Again, it is 0.8725. I think that's end of the problem, because they were only asking find the pressure once we remove the partition. Okay. All right, water is being heated in a piston cylinder device. Piston has a mass of 40 kilogram and a cross-sectional area of 150 centimeter squared. If the local atmospheric pressure is 100, determine the pressure at which the water starts boiling. Okay, so the temperature that the water starts boiling has to be the saturation temperature at that pressure of that system, your water. And this looks like actually a force balance question. So let's sketch it and explain. So we have a piston cylinder device, okay, and this piston is in balance, okay. And what does that mean? The forces acting on it has to be in balance. So the forces that are pushing it downwards has to be balanced with the forces that are pushing it upwards. And force that is pushing it upwards is basically the pressure of your system. What is trying to push it downwards is the atmospheric pressure acting on it. And also it has its own weight, right? This is balanced by the pressure of your gas. I mean the system. In this case, I'm sorry, it's not a gas, it's water pressure. Okay. So we can calculate the pressure of your water from a force balance, and this will require us remember what pressure is. Pressure is force acting at the point, force over area, right? So therefore, if I want to write a force balance, I need to represent that pressure in terms of its force. So I need to multiply pressure with area. That is the reason they give us the cross-sectional area of the piston. Okay, which is okay. Now atmospheric pressure is also given, 100. Let's write it down. And mass of the piston is given. All right, now the force balance is basically the force of the air plus the weight. Weight itself is a force, weight of the piston. is balanced by the force of your water. And of course, to force, we can write it in terms of pressure times area. Okay, dividing each term to area, we have remember, our goal is here to figure out the pressure of the water in our system. We can do that. Let's plug in the values. We have 100 kilopascal. Weight is mass times gravitational acceleration. So 40 kilogram times 9.81. This is a very wrong unit that I've just written. It is meter per second squared. And the area is already given to us. We need to be careful here about the units, okay, because kilogram meter per second squared is Newton. Newton per meter squared is Pascal. We know that 1 kilopascal is 1000 pascal, so we should multiply this with 1 kilopascal, 1000 pascal. Basically, you divide it to pass 1000 before you sum those terms up, because they need to be in kilopascal both. And if you do that, you find the water pressure to be 126.16 kilopascal. So now why this is important? Because at that pressure, we want the boiling to start, and boiling starts at this pressure only if it's at saturation temperature, right? So what we are looking at is the saturation temperature. So we need to find the temperature, saturation temperature at this pressure, because that is the temperature the boiling starts. Let's take a look at it. So we need water tables, and we need the pressure given to us. It was 126. Let's find it. Okay, we cannot directly see 126.16. We need to do linear interpolation to find the corresponding saturation temperature. All right, so I'm gonna plug these numbers here to show you that you need to do linear interpolation. The values we read from the tables: 125 kilopascal corresponds to a saturation temperature of 105.97, and when the pressure is 150, the saturation temperature is 111.35. Let's check again. Correct. And what we have as pressure is 126.16, and we need to find the corresponding temperature, right? So here you need to do, of course, linear interpolation. Let me briefly do it here. should be equal to and if you solve this relation, you should find temperature to be 106.2 degrees Celsius. And this is, let's check if it's in between these numbers. Yes, it is in between those numbers, so it's correct. Okay, so there is a piston cylinder device that contains 1.4 kilogram saturated liquid water at 200 degrees Celsius. Now the heat is transferred to the water until the volume quadruples and the cylinder contains saturated vapor only. Determine the volume of the cylinder and the final temperature. Alright, so initially we have saturated liquid and it's becoming saturated vapor. That is what we understand from this wording of the problem statement, okay? And initially the volume is, let's say, V1. Okay. And finally the volume becomes 4 times of this. Okay, this is also what is given. Now, let's take a look at state 1 and state 2, what properties we can understand from those states and read which tables we need to look at to read the properties. We are given the mass, right? The mass is 1.4. And what else we are given? Let's look at state 1. We have the temperature. And we also know it's a saturated liquid water. So these two is enough for us to be able to look at the saturated water tables and read the corresponding specific volume. Because it should be equal to the specific volume of the liquid, saturated liquid. So let's go to water tables and we are given it is at 200 degrees Celsius. This is VF and this is VG. So VF is 0.001157. Good. Let's copy that. Oy, that's not good. All right, now we know the specific volume and we know the mass. So you can find the total volume at the first state. Immediately we can also calculate the second state volume because it has to be 4 times of this. Good. Now what they're asking, let's take a look at it. The volume of the cylinder. So we already found that, right? I think volume of the cylinder at the final state is we found it. And also, let's take a look at what else they're asking, the final temperature. So the final temperature can be found from the tables, but to be able to look at the tables and read the right values, we need to intensive property at second state, and we can seem like calculate the specific volume. In addition to that, we know that it's a saturated vapor, so these two should be enough. Okay, so specific volume at the second state is the volume at the second state over the mass. So 6.479. Okay, and we also know we have a saturated vapor. That means that the volume of the specific volume should be equal to the specific volume of the saturated vapor. This will help us to figure out what is actually the temperature is. So let's take a look at table A4. Table A4, okay, and locate our specific volume here. Okay, so our specific volume is around 0.0046. So somewhere in between here, 0.004 6 to 8, right? It is in between those values, so the temperature has to be in between 370 and 373.95. Again, we need to do linear interpolation. Okay, so if you do linear interpolation, here is the temperature you read and the corresponding specific volumes you read for the saturated vapor. For 370 degrees Celsius, we read this as our specific volume. And also for this temperature, we read another specific volume for the saturated vapor. Now what we are looking at is our specific volume is this, and what is the corresponding temperature. If you do linear interpolation here, you should figure out your temperature should be 371 degrees Celsius. Okay, so a mass of 10 grams of oxygen fill a weighted piston cylinder device at 20 kilopascal and 100 degrees Celsius. The device is now cooled until the temperature is 0 degrees Celsius. Determine the change of the volume of the device during this cooling. Alright, so oxygen is an ideal gas, and they give us some properties at the first state, which is 20 kilopascal and 100 degrees Celsius. Let's sketch those. And this is the first state, right? After that, what happens is the volume is changing. And the pressure, we are given the temperature actually to be 0 degrees Celsius. We don't know anything else in here. So determine the volume change. Okay, so we need to find the volumes at the first and the second state, right? And these should be found from the tables where we can read the specific volume. Let's take a look at it. And the first, actually no, okay? So since this is an ideal gas, we don't have to look at the tables because the ideal gas equation of state tells us the relationship between the pressure, temperature, and the volume. So actually we only need to use ideal gas equation to figure out the volumes. All right, then we can do it because we know P1 V1 is mRT1, and if I want to calculate the volume, I need to do this, right? Mass is given. R is table A1. We read the R for the oxygen. But I don't have enough space here, so I'm gonna erase this and start again. So this is table A1. And T1 is in kelvins. I'm sorry, erase. It was 100 initially, right? 100 plus 273. So I did it wrong. And pressure is 20 kilopascal. See, you need to be careful here because kilojoule is kilopascal times meter cube. Therefore, the pressure unit has to be kilopascal and the temperatures have to be in Kelvin. If we are dealing with ideal gas equation, these are important points. All right, so here from here, I'm sorry, we calculate the overall volume. Very good. We can use the ideal gas equation for the second state too, because this time using second state temperature and pressure. Let's do that. Mass doesn't change. It's a closed system. R doesn't change because it is the same system, oxygen. The temperature change though, it is 0. Oh my god, my line is really bad. Okay. And pressure is 20. Now, why did I say the pressure is 20? Okay. Now, they didn't specifically tell us this is constant pressure process. But many times it is a right assumption to make where if this is a piston cylinder device and they are not talking about extra weight added on top of the piston, we should expect piston pressure inside not to change. Because remember, the inside pressure comes from the force balance. And if the pressure and the force acting on top of the piston is not changing, then it is okay to assume the pressure inside not changing with a piston cylinder device. And many times the right thing to do is actually in the problem statement mention that the pressure will remain constant, or it's a constant pressure process. That would be a correct way of wording the problem statement. But it's not a wrong assumption that you can make, okay? Then okay, let's see what they were asking. Determine the volume change. Okay, all right, we found second state volume, first state volume. It should be easy for us to calculate the volume change, right? But still, let's go to another page here. All right, so it's a negative volume because the volume has actually decreased. So it was compression, and volume has decreased, and pressure stayed the same, okay? There is a rigid tank. The volume is unknown, divided by a partition into two parts. One side is an ideal gas at 927 degrees Celsius. The other side is evacuated but has a volume twice the size of the part that is containing the gas. The partition is removed and the gas expands to fill the entire tank. Heat is transferred to the gas until the pressure equals to the initial pressure. Determine the final temperature of the gas. All right, so since we are dealing with an ideal gas, again, I would use ideal gas equations. So for the first state or the first region, we can write the ideal gas equation. Okay, so, and for the second state, you can write down the equation again. Now you need to notice something, right? For example, M and R are not things that are changing, that are constants in this process. Therefore, if you solve this for MR, this should be P1 V1 over T1. Same M times R is also and has to be equal to P2 V2 over T2. So since on the left hand side we have M times R, these on the right hand side, both equation has to be equal to each other. So P1 V1 over T1 is equal to P2 V2 over T2. So there are a lot of other things we can include in this information. For example, they say the pressure is not changing, okay? And they also give us information about the volume, because this is 1/3 and this is 2/3. So that means is V2 is equal to 3 times of the initial temperature volume. So instead of this, you can write 3V1. Okay. So with that, you can actually notice they also give you the temperature, okay, which is 927. But remember to use Kelvin. So this gives us that. Now basically what happened is 1 over this is equal to 3 over So T2 is therefore or. Okay, so let's see what they were asking. Determine the final temperature of the gas. So it seems like we're done. So the advantage of dealing with ideal gases is you can use the ideal gas equation of state to figure out the properties of the ideal gas, and we don't have to look at specific tables. So this is an easy way, therefore. Okay, a mass of 0.1 kilogram of helium fills 0.2 meter cubed rigid vessel at 350 kilopascal. The vessel is heated until the pressure is 700 kilopascal. Calculate the temperature change of helium as a result of this heating. Okay, so basically they give us initial and final properties of that ideal gas, helium, and all we have to do is use the ideal gas equation to figure out what they're asking for. So in the first state, we know the pressure, the volume, and the mass, and we should be able to calculate the temperature because P1 V1 is equal to MR T1. T1 is therefore P1 V1 over MR. And we can figure this out from table A1 for helium. Mass is given, V is 0.2, the pressure is given. So it looks like I can actually use this equation. So let's take a look at it. Being very careful with the units, the pressure has to be in kilopascal, the volume in meter cube, the mass is in kilograms, and R we should be able to look at from table A1. Let's take a look at it together actually, in case you're wondering how that happens. Is table A1 is here, we find helium here, right, and R is right there. Okay, 2.07969. We can also read the unit, kilojoule, kilogram, Kelvin. Okay, calculate it. So we were able to find the temperature. If we can find the temperature at the second state too, we can able to subtract them and find the temperature change. So let's take a look at if the same equation works for us. This is a closed system, so M stays the same, R is the same. The volume doesn't change because it looks like a rigid vessel. And the pressure at the second state, they give it to us, 700. Well, actually, if you guys just take a notice of this, V and M and R is not changing, but seems like the pressure is doubling only from 370 to 700. So you should expect temperature to basically double, okay? So it should be 674. Very good. So the temperature change is of course you know the answer, but still I'm writing. All right. Okay. All right, so 100 kilogram of refrigerant at 200 kilopascal are contained in a piston cylinder device. The volume is 12.322. All right, let's sketch it. We have a piston cylinder device. The volume is 12.23322. It's a refrigerant. And the mass is given. The pressure is given. The piston is now moved until the volume is 1/2 of its original size. Okay. So the half of the original size, right? Okay. And this is done such that the pressure doesn't change. Determine the final temperature and the change in the specific internal energy. All right, so this is refrigerant. They're asking for properties of our system, and we need to look at the refrigerant tables for that. And let's analyze the first state and the second state. In the first state, they give us the pressure. They also give us the specific volume, because you can calculate it, right? The volume over mass. Why this is important? Because once we know pressure and the specific volume, we can look at the right tables. So let's take a look at the tables, refrigerant tables. At 200 kilopascal, what is the specific volume? It's gonna be fast, I'm sorry for that, but we need to find the refrigerant tables. Here, the pressure one, right? Because they tell us it is 200 kilopascal. Okay. 200 kilopascal, making sure I'm looking at the right table. And the specific volume we have is 0.123, okay? It looks like it is bigger than Vg. So that tells me I actually have a superheated vapor. So if that is the case, we need to look at superheated tables to read the internal energy, okay, specific internal energy, because we need this information. Let's go and choose the correct tables. Superheated tables, the pressure is 0.2 megapascal here. And then we are looking at volume of 0.12. Let me see. This is very close because we have 0.12322, which is actually not close, exact. Okay, so that means the corresponding internal energy, we can read it. 263.09. Okay. Good, now we can look at the state 2 properties. At state 2, what are we given? The pressure. What else we are given is actually the specific volume, because it should be the half of it, right? Half of this volume. Since mass doesn't change, if volume is becoming the half of it, that means specific volume is also the half of it, because the mass doesn't change. So what I need to do is, if I know the specific volume at the first state, I need to divide it to 2. Now let's take a look at 200 kilopascal. Again, let's erase everything here, it's so crowded. Okay, so at 200 kilopascal, if we look at VF and VG, and our volume is 0.06 at the second state, it looks like it's in between. That means we have a mixture. Okay, so the specific volume we have is in between VG and VF. So at the second state, you have a mixture. Well, if you have a mixture, then you need to be at the saturation temperature at that pressure, because that's the only way there's a phase change. There's boiling going on, right? So the temperature, therefore, the saturation temperature at that pressure, which is minus 10.09. All right, so they were, I think, asking for the temperature and then the internal energy change. So the next thing we need to do is find this, right? But finding this is gonna require us to calculate the quality, because it's a mixture. I cannot directly read this from the table. Therefore, we need to calculate quality at the second state from a known property, which is the specific volume in this case. All right, the second state internal specific volume is known. It's here. And VF is this one, and VG is this one. VFG is VG minus VF, right? So the quality is basically 0.6135. Now we know the quality. I can calculate the specific internal energy using quality. And here UF and UG, you read the same tables, right? This is UF, this is UFG. All right, you just need to plug these in. That's it. Next thing is we need to subtract the first state from the second state, specific internal energy. And the final answer is there's a decrease in the internal energy, and that is an amount of 110.6 kilojoule per kilogram. And that finalizes our problem.